Hello, everyone. So I will again start with the general instruction. I welcome you all to the 2024 IEEE online forum on climate change technologies. Thank you again for participating in this event. For your information, copies of the presentation will not be shared. Instead, check back later the OFCCT website for the on-demand recordings of each session. Please submit your question and comments via the chat box. And with this brief instruction list, I would like to introduce our speaker, Dr. Luisa Petti, very briefly. So Dr. Luisa received her MSc in Electronics Engineering from Politecnico di Milano, Italy in 2011. She obtained her PhD in Electrical Engineering from ETH Zurich, Switzerland in 2016 with a thesis entitled Metal Oxide Semiconductor Thin Film Transistors for Flexible Electronics, for which she won the ETH medal. After a short postdoc at ETH Zurich, she joined First Cambridge Display Technology Limited in October 2016 and then Flexenable Limited in December 2017 in Cambridge, UK as a scientist. In 2018, she joined the Free University of Bolzano, where she is Associate Professor in Electronics since March 2021. Luisa's current research includes the design, fabrication, and characterization of flexible and printed sensors, energy harvesters, and thin film devices and circuits with a focus on sustainable and low-cost materials and manufacturing processes. Luisa serves as the member of the IEEE EDS Board of Governors, General Co-Chair of the IEEE International Flexible Electronics Technology Conference 2024, Associate Editor-in-Chief of IEEE Journal on Flexible Electronics, and as Associate Editor of IEEE Transactions on Agri-Food Electronics. With this brief introduction, I'd like Luisa to present his lecture today. Luisa, the platform is all yours.
Thank you very much, Mitradip, for the nice introduction, and thank you and all the organizers for inviting me to this nice event. So, as you see from the title, I'd like to talk about our recent work here at the University of Bolzano in South Tyrol on unconventional electronics for smart sensing in view of a sustainable future. So, I think we're all familiar with what conventional electronics enables and what performance can be achieved, but we're also aware of the limitations for certain applications. So clearly, we're looking into devices, put the pointer, which are planar, bulky, rigid, and invasive. Whereas unconventional electronics, and here I'm talking about flexible, stretchable, printed as well, but not necessarily only printed, and in general also sustainable now. Recently, electronics is enabling new functionality beyond, let's say, high performance electrical parameters in terms of conformability, in terms of lightweight, in terms of deformability, and also imperceptibility. And recently, we're looking not only into unconventional electronics, but we are really interested into profiting by the fact that these technologies are already use thin films, functional materials, which are not crystalline and bulky materials. And that's why they're more prone now to sustainable electronics. And so we're looking really into reducing, and I think that's really the focus also of this conference on climate change technologies. We're looking into electronics which has less pollution, ideally no pollution, less electronic waste. I think that's a huge topic, but also plastic waste and also use of materials that require mining. And that has in general a negative impact on the environment. So we're looking into materials and technologies that are natural, ideal, that are biocompatible, functional, and also enable biodegradability or transient behavior with different materials, clearly, so with a different palette of materials. And that ideally might also have a positive impact on the environment if well designed. So that's the vision and let's say the goal. We see there are many advances, but I think there is lots to do in this regard. So that's part of a EDM magazine, Electron Device magazine, on sustainable technology based also on oxide semiconductors, which is actually the topic of my previous work and also some of the current work. Of course, this technology now enable a lot of different applications. So on one side, smart textiles and garments, health systems, that's very important, soft robotic skins, wearables in general, also for various applications, smart consumer devices, and very recently this very important area of agri-food, which is becoming very interesting for this sort of technologies because it's really a natural platform where we interface electronics with our environment and we do not want to add more waste in our environment. And the way we try to work on unconventional and sustainable electronics in the Sensing Technologies Lab that I'm coordinating here at the University of Bolzano is to work from the materials to the applications. So we work mainly with materials that we either purchase or are, let's say, prepared, synthesized by collaborators, because we're clearly more engineers than chemists or material scientists, but we work a lot on the fabrication on and with sustainable materials. On the printing, because clearly printing as compared to microfabrication has a lower impact, so less carbon footprint, also energy required, more rapid prototyping. So let's say printing definitely has a lot of advantages. We're looking into the development of devices, electronic devices, which means a lot of sensors, because sensors are clearly the first layer of every decision support system that might be used in agriculture or in the food sector, or in wearables as well. So that means a lot of sensors and biosensors, but also actuators, which are clearly very important. We work also on the electronics, on thin film transistors and circuits, using both organic and inorganic materials. So I think we have a pretty agnostic attitude towards the materials, and the materials need to be useful for the application they are envisioned for, and that's to develop either fully flexible sensor systems. That's ideally the goal, to do everything, but that has lots of limitations in terms especially of frequency and though transmission and also computation capabilities, and of course we use also hybrid electronics, which means something flexible, unconventional, sustainable, close to the application, but then connected anyway to an IC or a rigid system to do all the computation and the transmission that requires more performing electronics. So both approaches actually. For various applications, so we work still on wearables for clinics and sports application. This is an example of a wearable triboelectric generator. We work also on smart garments for athletes, monitoring, let's say, parameters related to muscular activities. I'm showing this work actually in the presentation where I'm not showing the triboelectric, which we also made sustainable from waste, actually, so circular. We work also on bioelectronic interfaces, so interfaces of materials, mainly organic, with cells, in vitro cell systems, cultures and co-cultures of cells, and also inside the plants. So materials also to to augment the performance of the plants, especially in terms of biomass, growth, and these parameters. I'm not showing really part of this work because I want to focus mainly on these two aspects above, so the wearables, but especially the sensors for agri-food applications, which means plant transpiration and humidity, but also in general plant health application and food. But this is part of the presentation. We work also for sensors for food and water quality and safety, which means sensors for micro and nanoplastics in the water, but also packaging, which is very important. And also recently in this in vitro simulator of the gastrointestinal tract, trying to use our gas sensors inside this system. That's a little bit more general on the topics we're working on. And the approach to sustainability is double. So on one side, we use sensors which are flexible and unconventional to improve sustainability, so reduce food waste, improve plant health, and in general crop growth. But on the other side, I think the most powerful approach that I want to show you also towards the end of the lecture is actually bringing sustainability directly inside the sensors and the electronics. So develop devices which have a reduced carbon footprint and electronic waste that are green and degradable, especially in application where degradable is needed. Clearly not in every application this is needed. And use this to reduce food waste in a truly circular approach. So I think that's really where we want to head to with applications that allow lower performance. This is clearly the case. That's the outline of the topics that I would like to show you today. So starting from the wearables, in our case, especially for sports application, moving to bioimpedance for fruit and plant monitoring, which is a very interesting topic that many in the community are exploring now, to the printed sensors for, I call it also wearable plant monitoring, because it's really wearables for plants that we are envisioning, to the biodegradable thin film sensors and the circular laser-induced sensors. But let's start from the beginning. So this is the general picture of what we are trying to do is to sensorize our body with wearable and printed devices. And that means garments, electrodes in general, smart watches, active soles. So many parts of our body can be sensorized and have been sensorized in the last years. And here many things can be are interesting to be detected depending on the use case and specific application. Of course, you see also here, we in this specific case of this project that I want to show, we were mostly interested into breathing rate and sweat analysis. So those two main parameters, because this is part of an FFS project, so European Funds for South Tyrol, a collaborative project which ended recently between the Free University of Bolzano and various companies, in particular Microgate, which is a company working on sensors for space, but also sports application, together with another sister company, Microphoton Devices, Promotos, which is a sports facility also for rehabilitation, Tex Market, a textile company, and also medical doctors, sports related to sports from the University of Verona. So the title is Smart Textiles for Monitoring Muscle Activity. And with the first part of the project, we really analyzed in depth the requirements. The main objective of the project was really to monitor muscular fatigue. So when do athletes, in particular cycling athletes, start to have muscular fatigue? Can we detect this with a low-cost technology, real time, and really have a feedback on this, on the happening of this of muscular fatigue. And with the medical doctor from the University of Verona, we identified these two main parameters as indicator of muscular exertion, so the breathing rate, and the concentration of ammonium ion in sweat, which is actually an indicator of the passage from aerobic to anaerobic exercise. The state-of-the-art devices in this respect are this very bulky masks and laboratory analysis. So this is definitely not what we're looking to. We're interested in smart textiles, which are breathable, which are washable, which are reliable, accurate, and precise as usual, that's needed, reusable, low power consumption. And we're also looking into sweat sensors, which are sensitive, again, reliable, accurate, and precise, wearable, and with a low power consumption. We started focusing on mostly on breathing rate, and we looked into an extremely easy sensor technology, basically strain gauges, so resistive sensors placed close to the chest in order to be able to detect the chest movements, which basically account for a circumferential strain between 4 and 10%. And we did this using very completely printed devices. Basically not printing on textile, so we didn't choose to print directly on textile, but we decided, in this case, Martina was the researcher responsible in the project for all the experimentation. We decided to work directly on TPU with a carbon paste, which was screen printed, so the same technology used for printing of the logos of our t-shirts. So a very nice technique for mass printing also when used in larger scale, of a stretchable carbon paste on a thermoplastic polyurethane substrate. Moving on, the stretchable encapsulant, so everything again screen printed and encapsulant, and then shaping the sensor and laminating it. This is laminated with heat lamination, basically ironing, similar to ironing on a textile. And the textiles are the textile from the textile company that I mentioned you. So textiles used for the t-shirts of the athletes. This is how the first prototypes look like. Now this is integrated into a t-shirt, but with the U shape, which clearly is better in terms of stretching. And everything as visible, screen printed. Everything was first characterized in the lab as usual, so looking at a similar pattern of what we have in terms of inhalation and exhalation, with the same stretching rate, and measuring everything in a customized stretching machine that we have in our lab. So we tested these two textiles, so the Chrono and Asteria Pesante, if I remember well the name, and those are the enlargements of the patterns of the two different sensors. So this is all highlighted in this proceedings of the IEEE sensors in 2021. From that, we choose the best textile and moved into testing a sensor on a stripe, so very early prototype, connected to a portable readout system that was developed by the company, and testing this with a test protocol that was validated with the medical doctor, Silvia, that you see nearby here, of course, with the golden standard of this very bulky and cumbersome mask. So 5 minutes of regular breathing, cycling 5 minutes, and then recovering. This is all tested at Promotus, as reported also in this IEEE FATC proceedings in 23. This is the resistance change over time for the various phases, so the rest, the cycling, the recovery, and from those patterns, we can clearly see that there is a variation of the parameters. So in terms of breathing rate, what you can see, from the resting to the cycling and then the recovery in terms of breathe by breathe period. So this is all patterns that were able to be distinguished. Of course, here there are now various challenges that we still need to tackle in terms of stability, in terms of washability, which is definitely, so Martina tried to wash this a few times. That works for, I think, 5 times maximum, but then the t-shirt is, the sensors are basically released. I don't have now the picture of the final prototype. And the other direction that we went to was actually looking into ammonium ion sweat sensing. And in particular, not anymore in terms of textiles, but in terms of a smartwatch. And in terms of a more complicated sensor technology, more interesting as well, I would say, and in particular with an electrolyte gated field effect transistor. You see here the structure of the device, which has planar gate, source, and drain electrodes. It has a spray coated, so again printed carbon nanotube random networks of a layer of random network of carbon nanotubes, single wall carbon nanotubes, and it has also a membrane because we're interested into selective sensing of the ammonium ion and an electrolyte, which is clearly, let's say, leading to the operation of this device, which do not have any solid dielectric as a traditional transistor. What you see, so the device has a polyimide, chromium gold source and drain, the carbon nanotubes, and then the electrolyte. This is the structure again. How does that work? So we, if we apply a negative gate, because in this case the random network of carbon nanotubes is actually behaving as a p-type semiconductor. So if we apply a negative bias at the gate, what happens is that within the ion-containing solution, so the electrolyte, we have a rearrangement of the ions, so positive ions towards the gate and negative towards the channel, which leads to the formation of a double layer, so 2 electric double layers, so one at the interface of the electrolyte, which in our case we want it to be sweat because that's where we want to do the biological detection of the ammonium ion, so the detection of the ammonium ion, and another electric double layer at the interface with the semiconductor. The distance is called the so-called debye length, is very small, and that means that we have a really large capacitance, both at the electrolyte gate interface and at the electrolyte channel interface. And in that way, what happens is with this rearrangement, the bulk of the electrolyte behaves as it would be the gate electric of the field effect transistor. So that's a little bit the structure. The structure is similar to organic electrochemical transistors. The only difference here is that we have a semiconductor. The difference is that the semiconductor is not a mixed ionic electronic conductor, but it's only an electronic conductor. So we have no diffusion of the ions inside the semiconductor, and there is no contribution of the ions to the transistor conductivity. This was nicely reported in this applied physics review by Bulia and Mattia, that were the main researchers working on these technologies in the lab. The interesting part is it's really also the membrane, because if we use now an ionophore, so an ion selective membrane, in this case for ammonium ion, because that's what we're interested in, what we see is that from all the interfering ions that we can have in the sweat, only ammonium ion is able to diffuse and enter and get in touch with the carbon nanotubes and do lead to a variation in the transistor current that can be read and correlated to the difference in concentration of ammonium ion. This is the fabrication, so it's not fully printed. because we are evaporating the chromium gold electrodes on polyamide, so on plastic substrates, and we're doing a lithography and lift-off process. Then we are printing, so we're spray depositing the carbon nanotubes. We're drop casting the membrane, and that we're doing a membrane conditioning. That's very important to stabilize the sensors. And this is how it looks like. So we have this geometry with these big pads, because sometimes we also functionalize the gates. In that case, is less needed. But you see the interdigitated source and drain contacts and the carbon nanotube between the contacts. And this is before the electrolyte. The membrane, as you see here, the drop casted membrane, and this now gets chamber, and the sweat is actually then added in order to connect this whole area. This is shown a little bit here. So we have the sort of PDMS chamber where the sweat is actually the artificial sweat, because we're doing most of the test with artificial sweat, so mimicking the sweat characteristic. And then the different solution of ammonium concentration are added in order to calibrate the sensors. Everything, as you see, is tested with a probe station and a parameter analyzer. And you see here also the pipette. What you see here is that you have first time where you need to form the electric double layers, but then there is actually a change in the variation, which we are actually calculating, so doing a baseline fitting in order to remove the stabilization time, which takes more than an hour typically. And then what you see here, we do the pipetting of the different concentrations of ammonium ions. So from 0.01 millimole to 100 millimole, those are the level of interest for the application we're looking at. But interesting is also to see that being an electrolyte gated transistors, the operation voltages are very small. So what you see, this is the stabilization phase. Then we have a constant slope phase. Stabilization is typically an hour. And if we do a baseline fitting, we can really then measure only the variation in the current, the increases in the current in this case for the different concentrations. This you see a little bit better, this PDMS chamber that I was mentioning. Okay, this is the concentration of interest, and this is the characterization in the laboratory. So we first measured with water, with both conditioning in the membrane conditioning and not. So membrane conditioning is always good. We also measured in artificial sweat, conditioning again the membrane in artificial sweat, and we get a pretty linear behavior with a good sensitivity and a good also linearity of the sensors. This work was then continued. In this case, Mattia was the main researchers working on this. Was continued also in collaboration with the group of Sandro Carrara at EPFL, where he, in view of the development of a smartwatch, he worked on the full readout system on a flexible PCB with transimpedance amplifier, a microcontroller with Bluetooth connectivity, and a battery, in order then to realize, of course, also microfluidic is needed. And this was actually just awarded at IEEE Sensors, the prize for the best paper in IEEE Sensors letter of last year. It was also tested in different bending of this flexible PCB. Good. Let's completely switch gears. And I need to move a little bit faster now. I see that I'm slow. I want to show you a little bit the work on bioimpedance for fruit and plant monitoring. I think electrical impedance spectroscopy is an extremely interesting technique that is used in a lot of applications. So also medical. We're working also on impedance plethysmography with bioimpedance, food, biosensing, because a lot of the biosensing, if we read the full impedance spectra, we gather way more information. Clearly, we need more complicated electronics and more consumption, but this is, in many cases, really worth it. We use it a lot for fruits and plants. And I mean, I don't think I need to explain what bioimpedance is, but the way we use it for biological interfaces like fruits and plants is really to apply an AC voltage at different frequencies to a biological tissue and measure the resulting current, and trying to fit this with an equivalent circuit model that tries to understand a little bit better what's happening inside. It's clearly a black box approach, but it's a very powerful black box approach. So a typical fitting of a component like an apple could be is a so-called Cole model, which takes into account the resistance due to the intracellular fluid, the capacitance of the membrane, and the resistance of the extracellular flow, which actually has different behaviors at different frequencies. So at low frequencies, the current path is in the extracellular space, what you see here blue, whereas at high frequency the current can pass through the membrane structure. So you can see different things at different frequencies. What we are doing now is using this for fruit, so non-contact but non-destructive fruit damage detection, but also plant stress monitoring. And in particular, this project in collaboration with Langburg, Sundus, and also Pietro are looking at, can we use bioimpedance for the monitoring of the apple quality to increase its live-shaped apples are really important in South Tyrol, and assess the internal damage of fruits throughout the whole supply chain. Of course, we want to have something healthy, which has an intact cell membrane, a high capacitance, an extracellular matrix intact, and also instead of something with internal browning, which typically you recognize only by destroying the apple, because it's something you don't see. Typically, you don't see much, at least when it starts from the outside, where the membrane is disrupted, and you have different behaviors, different water content as well, and do also different conductivity. This is the setup that we are using. We use for the sort of feasibility studies, really ECG electrodes. Those are the best working solution when we want to find out if a technique is suitable to detect something. Of course, we're working also on printed electrodes, dry electrodes, that's a very hot topic, and sustainable electrodes. Ideally, on the apple, you would like to have edible electrodes, right? So that would be the dream in the future. An analog discovery setup, and then a GUI, a graphical user interface on LabVIEW. To classify the data and do supervised machine learning with the data that we acquired, lots of data, what Sundus did here with our agricultural center is to divide in 3 classes: healthy, slight brown, and severe brown, and you can see it only, as you see, only if you cut, and also doing destructive tests in order that an expert team is able to discriminate this and label the data. Sample data ambiguous were excluded, and that data set had 20 sample data for each class. Now she's doing more experiments and also learning from clearly the mistakes of the first experiments. These are the impedance spectra, so the magnitude and the phase for samples which are healthy, slight brown, severe brown, for different frequencies. And here at this particular part of the spectrum, you can see that you can see the difference between the healthy and the other classes, which have internal brown, especially the red data. If we look at it at different frequencies, so the 40 hertz, the 10 kilohertz, the 2.5 megahertz, you see that there is clearly possible to distinguish between, this is a statistical ANOVA test, so it's clearly possible to distinguish between healthy and between non-internal brown and internal brown, especially at low frequencies, whereas so these two parts, whereas it's at the moment is not really possible to distinguish between slight and severe brown. So she's really continuing now Sundus this work, which I think is really nice to show that with bioimpedance, with electrical impedance spectroscopy, you can also detect internal browning. So this was presented at IEEE Agri4 and published in the transaction on agri-food electronics this year. What another project, which was in collaboration with the Italian Institute of Technology, done by Selene and Pietro, is to work on plant stress monitoring. And in particular, using, in this case, really needle electrodes and inserting this inside the stem of tomato plants. So we worked on tomato plants to look into both water stress, but also iron stress. This is the setup in our greenhouse that we have in Limburg, so again, close to Bolzano, with a set of plants with standard conditions, a set of water stress plants, and a set of iron stress plants. Again, analog discovery, multiplexer, Arduino, and with this, measurements were taken every hour for a total of 30 days of experiments and acquiring more than 1,000 impedance spectra for each plant, so lots of data. You see here the magnitude and phase for control, early stress and late stress, and that's in the case of the water stress, and that's in the case of the iron stress. And acquiring really more than 8,000 spectra in both cases. What was done here was first a fitting to the cold equivalence circuit to look for statistical differences, so similar to what Sundus has been doing for the apples, and this was again presented at the conference on agri-food electronics, the first conference in Turin, and published in Computers and Electronics for Agri-Food. But very interesting, we went here further. So what really Pietro is doing is to look into a simplified procedure for classification with machine learning. So taking the bioimpedance data, but also environmental data from the greenhouse, fitting the parameters, and then applying different classification algorithm to these categories. And this was again published in recently in IEEE transaction on agri-food electronics. This shows that the machine learning perceptron, the multi-layer perceptron algorithm is the one that is able to give the best results. And I think there is way more that this technique can really do, which is extremely powerful, I have to say, although being a black box approach. What Pietro was also recently working on is to trying to do that also on plant. So, I mean, not only post-harvest, but also on plant, with the vision of creating, I think in the future, smart gloves, but also smart robotic systems that can measure the level of ripeness through bioimpedance. We showed already in the past that bioimpedance can be used for ripening measurements, both on plant and post-harvest. But what we want to show here is a full glove system integrated. And this was again in collaboration with the Smart Material Labs at the Italian Institute of Technology in Genova, where we developed a textile glove integrating a portable impedance analyzer. This is a perfect example of hybrid electronics because this is standard electronics. Spray coating TPU carbon nanofibers on a fabric substrate. Of course, we did lots of electromechanical characterization from static stretching to dynamic, because the glove clearly is sees a lot of stress when used. We did grasping tests. So here you see the printed electrodes on the glove the connection is still very rudimental, but that the glove is able to do and to detect bioresistance changing grasping. We compare them with the standard ECG electrodes, which are our golden standard for bioimpedance. And what you see is that we really need to use the gel. So we are still way before the development of dry electrodes. So there needs to be a lot of work still done to realize. So you see that the fabric with the gel is very close to the ECG, although up to certain frequency. So there is a reliability limit which needs to be taken into account, but this is okay because the upper limit of frequency measured with this portable impedance analyzer is 100 kilohertz. So we did tests on strawberries, on plants with these electrodes, and you see here the realized, the magnitude and the phase, with the curves following expected trends and values for strawberry fruits. And this was recently presented by Pietro at the IEEE IFTC and also published in the Journal of Flexible Electronics. Good. That was, I think, a bit of an overview of bioimpedance. Of course, there is not only bioimpedance. We can think also of simpler sensors, or we can use simpler sensors, and that's what Saira has been focusing extensively recently, as shown also in a conference of agri-food electronics and in transaction of agri-food electronics. Also in CAFE this year, actually, she showed the system integration perspective. And here she is working on fully printed, so this is dispense printing, so a digital printing technique, super easy, super low cost, no mass need, low prototyping, low ink use, so very nice technique, on a filter paper, so a cellulose paper, filter cellulose paper using PEDOT-PSS, so an organic material, and looking at the impedimagnetic relative humidity, so the impedance change, again, impedance, and the principle of operation is basically the absorption of water and the change in the impedance of the device. So this is the layout, calibration. She did lots of calibration in, this is in Granada, in a climate chamber, showing calibrating the sensor. And then she showed the sensors tested in various locations of plants. These are tomato plants again. So in proximity or to the plant, so more or less humidity, on the leaf surface and on the leaf bottom, and clearly also comparing them. This is in the greenhouse, comparing them with reference electrodes and testing them on different tomato plants to try to see if she was able to monitor the plant's microclimate, humidity, as well as the potential transpiration of the leaves. So you see also the alternation of day and night and the different sensors. Now the project moved on a higher TRL, and she applied the sensors in an open field. This is Lido, so Limburg Digital Integrated Orchard, so apple orchard, and she's testing the sensors in the field and acquiring lots of data. And then we are looking into assessing the performance in such harsh environments, validating the suitability of the platform to multiple sensors, and comparing also Bayer and PDMS coded sensors, evaluating sensor lifetime and in general plant health monitoring. And this is part of the PNNR Agritech project, PNNR funds in Italy. Okay, moving quickly to have also a bit of time for questions that I see are coming up. I want to show you really the last approach. So really the circularity and the sustainability in the sensors. So what we do is more sustainable, but still not fully sustainable. And that's what we're trying now also as part of this national project PRIN, together with the University of Venice and the University of Modena and Reggio Emilia, called Bytes for IoT, so biodegradable thin film electronics for IoT. We're trying to work from the materials and fabrication up to the final application on biodegradable thin film transistors and circuits, so more than sensors. We're not there yet, so what we worked a lot is on temperature sensors, easy temperature sensor on a biodegradable chitosan substrate. So chitosan is extracted from the crab skin. So in Venice, they develop the process for chitosan. Realization is what we do is we spatter. This is at the moment a completely dry sputtering process. So we sputter through shadow mask, both only resistive temperature detectors, so RTDs, but also thermistors with an indium gallium zinc oxide semiconducting layer to develop temperature sensors that you see characterized in here. And this temperature sensor, I wanted to add the degradation picture, but I forgot about it. But this sensor is are completely transient, so they degrade in water, in citric acid and juice, lemon juice, but also in water. So we're working now on the dielectric, on the optimization of the dielectric in order to be able to develop transistors as well, and also on a transfer process, so to develop on rigid substrates and then transfer the electronics on every type of substrate, which, as you imagine, has a lot of issues in the fabrication. Last but not least is also a very interesting work that was done mainly by Giuseppe Cantarella, who's now at the University of Modena and Reggio Emilia, to develop paper-based, completely circular electronics, and working on this commercial paper substrates that can be purchased by Favini, by a paper company, and that are, let's say, prepared from kiwi, apple, and grape leftovers, and showing that we can also fabricate with the laser. So we can carbonize the surface of a laser we can carbonize the surface and make it conductive using a CO2 laser. This is a technique a lot used. I completely forgot about the reference. I apologize. So this is not from our group. But this is a technique that is well used in a lot of different groups, especially on polyamides. And here we showed it on paper substrates. And here we showed some very simple electronic components, so really basic. So ECG, so electrodes for heart rate and respiratory activity, also electrodes for bioimpedance, for food monitoring, capacitors by graphitizing, carbonizing one part and the other part, and using the remaining paper as a dielectric. And then showing how this can lead to completely zero waste. So in lemon juice, after 40 days, this is completely dissolving and degrading. But it could also be used or reintroduced in nature by using it as a substrate for seeding, seeding so let's say this is a carbonized substrate. We use some seeds and then we show that it allows germination. So it could also be used as a substrate for plant growth. And I think this shows really the power of this completely green and circular approach. This received also the cover page from Advanced Functional Materials. With that, I think I'm at the end, at the acknowledgement. Of course, this work was done by a lot of people in the group and a lot of collaborators. I need to thank a lot Martina, now at the European Patent Office, Mattia and Infineon, Bulia, Sundus, who's still here. Bulia actually also left. This needs to be updated. Pietro, Saira, Ahmed, and Enrico, who also left, and a lot of collaborators from Microgates, Verona, IPFL. I mentioned Sandro Limburg, Nassi Attanasio from IIT, Almudena in Granada, and so on. Yeah, and this is an old picture. We do tomorrow a new picture, so I don't have it today. And this is a list of collaborators and all the funding entities and agency I clearly need to thank. And I thank you for the attention.
Thank you. Thank you very much, Luisa, for this very interesting talk. So we have a couple of questions in the chat box. So one of the question is, I think you already have addressed this question in the last part of your presentation, but I'm still reading it out just in case if you have any additional comments. You addressed the e-waste problem briefly. How specifically do we address this very real and growing problem? For example, with the sensors you discussed here. So I think in the last part of your presentation, you briefly have
Yeah.
mentioned, just in case if you have some additional comments.
Yeah, so I mean, this is really the future. It's really where we are trying to work on. It's not easy because clearly the performance drops, the level of complexity drops. I think, and I mean, e-waste, clearly that needs to be solved. Biodegradability is maybe not needed for many applications. So that's maybe something on top, only for special cases. Yeah, I think if in this project, we really want to address more complexity. In this last project that I showed, the print project, let me see if I can go back. Oh, okay, maybe I need to, okay. In this last print project that I showed here, really the goal is to develop more complex electronics and try to substitute everything. You see, it's not organic, so we are trying really to put it on the inorganic. Yeah, I mean, indium gallium zinc oxide still has indium, so it's maybe not the best choice, but we're trying to work it stepwise. So let's try to use metals that are less harmful, as in the picture that we saw before. And let's try to substitute step by step with a palette of suitable materials. Sensors are easier to do in this way, but more complex transistors and dense circuits are anyway more complicated.
Yeah, that's true. So our next question is, what do you think will be the main drivers for the large scale application of these unconventional sensors?
So we are working clearly that's a nice question, thank you. We're clearly working from a research perspective. So we have smaller printing tools. Our screen printer is still, not the huge screen printers that can be used. We purchase inks for our lab use. So we don't do large scale. So we're not. It's not our goal. But I think this is what companies that are working on printing can do. I think the cost of the inks needs to reduce because we always talk about low cost, but some inks are extremely expensive anyway. And you need to have facilities for printing on large scale. So then I think it really comes in terms of cost effectiveness, in terms of rapid prototyping. But that is something which in some cases has been shown, maybe for roll-to-roll printing of tags. This is an industry which has shown the potential, but for sensors, I think there is still way to do, and for transistors and circuits, there is a huge way to there. So, I mean, sputtering is also something that can be done on larger scales, but I think we are still mostly in laboratory scale. With the technology I used to work during my PhD on metal oxides, I think now with companies like Pragmatic that exist, we see that this technology can really lead to large scale applications. So they have this foundry model on this, you can order your circuits, and when we were developing them, the cost was way higher. So I think this can happen, but it needs a lot of investments and the right people to start companies.
Yeah, true. So you already have discussed the scalability issue in this answer, that there are some things that maybe for silicon technology, we have already built-in processes in place. But I have a very, I mean, related question, because we are or the kind of sensors that you have developed is unconventional. So every day new materials are coming in. So how do you take it in terms of the scalability? Because every day new materials are coming in, the processes are very different. So if you look at the future, what do you think that how this will translate into a maybe a large scale, which to some extent you already have discussed, but I just want to get an idea that what do you think, what will be the future in this kind of sensing technologies?
It's true, new materials are coming in, but in the end, there are already some candidates
Mm.
for specific applications. So I think silver chlorides for many electrodes, although not extremely good for certain things, are kind of the material. Also carbon inks. PETS is a fantastic organic materials used for bioelectronic applications. I think lots of new materials coming in, but there's nothing beating PETS for that application. So it's true they're coming in, but I think we already have some winner materials, or at least some good materials. And some processes are not so different when you change the material.
Mm.
So I don't see that as a huge issue, to be honest. Maybe I missed the point that you're I think it's less complicated than in silicon technology. I'm not a silicon person. I think I never processed on a silicon wafer, so I'm an unconventional person. Respect, let's say. But I think is not as complicated as in the silicon technology, and you don't need to change the tools. So I think it's also a more resilient sort of fabrication that does not need to be readapted constantly, like it happens in the CMOS industry.
Yeah, exactly. So the only thing probably is the changing this viscosity and all these parameter with the materials. Uh, Other than that, I think most of the processes are better than, or maybe
Not
easier than.
so big, the change, right? There is a change, it's clear. Every process needs optimization. But it's not as complicated as in silicon technology. And I think we have lots of new fancy materials, but they're more for a research publication than for final applications sometimes.
Yeah, that's true. That's true. So is there any other question from the audience? Because we have a
Uh,
few minutes.
I
Yes,
have one question.
yes.
Uh, I'm just awestruck. So much of work. I'm really happy to see that, because many of them are intuitive, and then you basically get into the field, and then you try to develop. So it's bottom up, if I'm correct in looking at it. So that's very much nicer, because that's when the value of the innovation comes into picture, according to me. So my question is, how did you get these innovative thoughts or ideas? Because some of our students here in this, I'm quite old, so I may not learn much, but at least for the students here in this call, they may be really looking for that. But of
I'm
course,
maybe
I'm
not
also
the
interested.
person that gets a lot of innovation, because I'm the one that does less of the research. So I think we have good students, yeah, that had good ideas, definitely. Most of the things come from collaborations, I think. So there is a lot of collaborative work. A lot comes from trying to find applied things for the territory. So here in South Tyrol, it's a special place. It's a small region which used to belong to Austria first before World War I. So it's a bilingual, small mountain area. We're in the middle of the Dolomites, so very agricultural and mountain. And we try to do things that are useful for the territory, because also lots of fundings comes from things applied. And so, you know, all the plant research started because of collaboration with the agricultural faculty and trying to connect to the territory. And when you start applying things, I think the fancy idea come because you see what is needed. I think there is still lots to do and lots of understanding missing, because our approach is an engineering approach. But I think we had also the lack of having a lot of students from different backgrounds, because we don't have a master in information engineering or or electronics. So lots of our students come from biotechnology, food science, physics, chemistry, biology as well. And I think that's where this intersection between competencies, the fancy idea, and arrive, I think. But that's, I think, the experience in the last 6 years here. So, yeah. I hope I answered to your question.
No, it's fantastic. Just a small supplementary thing. Do you have any of these devices, for example, because my expertise is in building systems, so I'm a systems guy. So in that sense, are there some of these devices or samples that you have built and then you moved on, but probably some of those samples can be utilized. Also for my master students, some of these courses we can ask. Of course, Mitradeep is actually spearheading one of those our sensor councils. Nice thing for students. So if there are some sort of things, I will reach out to you.
Yeah. So we have lots of things that we're not doing anymore because, of course, people leave. So you see the list of the people that of the work that I showed, because this is part of what we do. Clearly, the group is big, but most of these people left. And typically, when someone leaves, things change because there is a bit of things that pass from one to the other, but not so much, I have to say, because typically in academia, people leave quick. So there is not so much time. So there are lots of things that we don't do anymore of the things that I show. There are surely samples running around, but also a bit of the knowledge gets lost. So maybe more than a bit of the knowledge gets lost. So, but surely, I mean, we're not system integrator. We are device technologists. So every time that we do something more integrated, we collaborate because I'm a fake electronic engineer. I'm more towards the physics.
Sure. Thanks a lot. Yeah.
Thank you, Luisa. If there is any further question, I don't see any question now in the chat box. I guess you have addressed most of the queries. And thank you again, Luisa, for this wonderful talk.
Thank you.
And
Thank you for inviting me.
Charlie, it's over to you now. If there is any announcement or something that we need to make.
No, and most people have gone, but I'll invite everyone to join us starting December 2nd for this Monday, Tuesday, Wednesday, and Thursday for our next round of talk.
Thank you very much. Thank you, Luisa. Thank you, Charlie. With this, bye-bye.